Hi, welcome to another edition of Moment in Science. I'm Cameron Sahami.
And I'm Kachun Yu.
And today's topic is Bose-Einstein Condensation. We're doing a special two-parter with Dr. Carl Wieman, and this is the first of two parts. Kachun, would you like to
Well, Dr. Wieman is a professor of physics at the University of Colorado, and he's also a fellow of JILA, which is a joint institute between CU and the National Institute of Standards and Technology. And he got his PhD from Stanford back in 1977, and he's been awarded, he's a Sloan Fellow, a Guggenheim Fellow, Fellow of the American Physical Society. He's in the National Academy of Sciences. He's been awarded the Einstein Medal for Laser Science last year, or in 1995. And just a couple of days ago, it was announced that he received the King Faisal Prize for 1996, as well as the Science Magazine's Best Paper of the Year award. And so, welcome, Dr. Wieman.
Welcome, Dr.
Thank you. So, the work I'm going to talk about, if I can see the first slide.
Can we go ahead and turn on the first slide?
It's been going on actually over quite a few years, and I only do a small part of it. It's really a team of lots of graduate students and postdocs who are kind of fuzzy there.
Can we get it focused?
Actually, graphics.
This shows a little of the lab, and some of the students, which actually we have about twice as many who've been working on this project. The second slide. This is actually the co-leader, coach of the team, Eric Cornell, who's shared in all this work and all these awards and so on. Can you turn that off? The lights back on. So let me tell you about this Bose-Einstein condensation is a new kind of matter, a new phase of matter that you get at extremely low temperatures. And to understand it, you have to first understand temperature. That what temperature really is if you look at any object and you magnify it way up, you'll see that there's little atoms in there vibrating around. And temperature is really a measure, what we call temperature, is a measure of how fast those atoms move around. So you can imagine like the atoms in the gas here. They're just like these little ball bearings, except a lot smaller. And so when things are cold, these gas atoms are bouncing around, going sort of slowly. And then if I heat this up, they're going faster and faster and faster. So that's like fast atoms, and now they're getting colder and slower.
Hey, there's one that evaporated.
Right. And of course, the real atoms in the gas are much smaller than this. They're also going a lot faster. They're going about 1,000 miles an hour.
Now, when you're talking about phases of matter, phases that people might be familiar with would be, say, a gas.
Yeah, the normal things are gases, liquids, and solvents.
So those are the three phases?
Yeah, those are the ones we're used to. And now and what we're looking at is something that happens at much, much lower temperatures. So to understand how low a temperature we have to get to, you can show it on the next slide here. If you think about temperature as in terms of this motion of atoms, you see there's really there's a different scale than we're used to. So you see Fahrenheit over here. That's what everybody is used to. But in terms of this atomic motion, a more handy scale is what we call absolute, or the Kelvin scale. And the reason that's handier is because if you think about it, you can only get something so it's going so slow, and then it's stopped. And that's represented by the Kelvin scale. The zero really means something. Absolute zero is a very special place. It's where all motion is absolutely stopped. And that's the coldest you can get. You just can't do any better. So up in green, you can show sort of the range that the Earth, temperatures on the Earth can be at. And, even in the worst in Boulder last week, it's somewhere way up here. You can see relative to this absolute zero, we're pretty hot. And in fact, the coldest you can ever find in nature is when you go to the depths of outer space, and it's on this scale 3 degrees above this absolute zero. And temperature is one place where people can do an awful lot better than what you find in nature, because if I can see the next slide, you can see this 3 degree Kelvin. I've blown up this thermometer by a tremendous amount. So now this the coldest deep space, think of it as being up here about 20 miles high. And on that scale, the phenomena we're looking at, where we cool things down, we're having to cool them down to very down to just a little tiny scale down here in the bottom. That corresponds to about 100 billionths of a degree above absolute zero. So that's how cold we have to actually get things.
Wow.
That corresponds to slowing these atoms down from sort of a 1,000 miles an hour to something that's just barely creeping along, sort of a good snail pace.
And then I see the comparison you have there is 1 millimeter to 3 times the height of Mount Everest.
Right, and that's the comparison between what we cool things down to compared to the coldest you find in nature.
So that's a scale,
Yeah.
basically.
So, well, let me talk now about why we're interested in getting things this cold. And I think probably that's, it's really because of what happens when you get things super cold. And to understand what happens, you have to realize there are really two, you can probably have the lights on, but there are really two kinds of objects in nature. There's one kind called bosons, and the other kind called fermions, and everything, including atoms, falls in one category or the other. And they're named after two famous physicists, Fermi and Bose. Okay. Now, the thing that's interesting is that about 70 years ago, Albert Einstein noticed, just looking at the equations that describe these things, completely abstract sort of stuff, that the things that were bosons, the equation said if you got them really cold, some very radical, dramatic thing should happen. And nobody really thought very much about it because it was such an impossibly low temperature, and even Einstein just kind of commented, oh, funny equations, went on from there. But over the last 20 years, we've really we and physicists have been working to get things to this kind of cold. And to sort of illustrate the difference between bosons and fermions and what happens, you can think of fermions are the unsociable atoms. They really don't like to get too close together, okay? They want to stay apart. They're territorial. Bosons are the sociable ones, and they like to be together. And in fact, some manifestations of this behavior you can see in the world around you is lasers, the little particles that make up light called photons, which if this is still working just barely, you can see the light, this red light from this laser going out here. These little particles of light called photons, they're bosons. They all want to be the same, okay? So that's why lasers work. All the light goes in one direction, it's in exactly the same color. Some things that are fermions are like electrons that make up this chair, make up most of me, and they don't want to. They want to stay apart. So that's why I don't fall through the chair. Those electrons in me and the electrons in the chair don't want to have anything to do with each other.
What if you tried to squeeze these fermions together? Do they have a tendency to rebound?
Push right back very hard. Yeah, they can push awfully hard. So that's the way the world works the way it does. And so, but at normal temperatures, you never see these effects of bosons wanting to come together, and that's why we have to get things very cold. And you can understand this a little bit if I can have the next slide. This is an illustration of the difference. Think of fermions. Okay, fermions, they're sort of like bears, you know, they're territorial. They don't want to be in the same place. And so atoms also, well, so here's the bear. Each sort of has its own territory where it wanders around, and you can find it in that region. Atoms are the same way. They've got a region where they can be found. And if you make it colder so there isn't so much food around, those bears got to search over a bigger region. And if you cool down atoms, they do the same thing. They kind of get bigger. So fermions would be like this. They would all get, those territories would expand until they run into each other, and they'd start sniffing around, noticing there are other bears, and then they'd stop. They would each have its own territory, and there wouldn't be any overlap. But the next slide, you can think of buffaloes. They're like bosons. And so the same thing happens. They get colder, they wander over a bigger region. Now when these start overlapping though, and this is really what the equations were telling Einstein, when these territories where you can find the buffaloes, just think of these as like atoms start to overlap. Now what happens is, well, you know, if buffaloes start smelling each other, they like to come together, and so they collapse together. If you have the next slide, they collapse together into a tightly knit herd, okay, a tight little herd, and this is very much like Bose-Einstein condensation, sort of Bison-Einstein condensation maybe. But one of the big differences here is atoms go one step up on buffaloes. Namely, the real analogy would be if here you still see there are a bunch of separate buffaloes. In Bose-Einstein condensation, the atoms all really go to exactly the same place. We call this going to the same state. And so they're all exactly in the same place, moving in exactly the same fashion. So it's really much like if these buffaloes all kind of just fuse together like drops to find one giant buffalo, and we call this in Bose condensation, that's this Bose condensate, or sometimes called a superatom for just that reason. Now, in fact, it's been 70 years since Einstein predicted this, but there have been some things that we think are quite close to Bose-Einstein condensation in nature. Namely, you've probably heard of superconductivity, where electrons all flow with no resistance through wires when you get them cold enough. And there's less well known as superfluid helium, where you cool helium down and the liquid then can flow around and never stops. Okay? Both of these we think are manifestations of this same basic physics, although they're quite different than what Einstein was thinking about, because he was thinking of a gas, and those happen in liquids and solids. So what we really set out to do is to try and achieve this in a gas. And so what you've got to do is start with a bunch of atoms, and you want to make them very cold. That means, if you think about what I was talking before, means you got to get them very slow. And so we've many years working on this, trying to figure out how to get them slower and slower. And the first step in the process is we use laser light to actually slow them down. And if I can have the lights, maybe.
Wow, that sounds like a pretty interesting process, using lasers to cool something.
Yep. Yeah, you think of shining light on something makes it hot, like these lights. But it's really the effect of bouncing. I'm absorbing light and getting hot. We bounce the light off the atoms, and that makes them cold. And you can think about this as magnify up these atoms tremendously until our atoms, where'd my atom go?
I think it's right over
There's
here.
my magnifier.
Giant atom.
So imagine a giant microscope looking at an atom in the air here until it was that big. And now it turns out on this scale, little particles of light called photons, they look sort of like, they're about like this, sort of like a ping pong ball.
Okay.
And so you know that if you bounce this ping pong ball off a big ball like that, it gives it a little bit of push, right? You can maybe just barely
Pushes
feel
back.
it.
Sort of conservation of momentum.
Yeah.
We talked about that before.
Okay. So obviously, if you've got this atom though zooming along and you want to slow it down and stop it, you need a lot of these things bouncing off it. So that's what lasers are good for. They give lots of photons. So in the same way I've magnified up our atoms and our photons, here's a magnified up laser you can think of here. Have to get it pumped up here, ready to go.
A stimulated emission.
And so now here's my atom zooming along. In the same way I've made it bigger, I've also made it a bit slower, so it's not
Okay.
going to go 1,000 miles an hour.
Okay. Let's
Okay.
see if we can try and do this.
Okay, so you can see if you bounce a lot of photons off an atom, it gives it a pretty big push, and it can not only, it can slow it down, even turn it around. in this
like it
case.
did.
Okay, so the trick is, in laser cooling, is we take beams, then we've got a bunch of atoms, they're like this, they're bouncing all around. We want to send light in from all directions, so no matter what direction this atom's going, it feels this stream of light hitting it in the face, bouncing off it, wanting to make it slow down.
Wow, so it's trapped by all the light around it, basically.
Well, first it's just slowed down. The trapping part is, if you want to get something really cold, you've got to make not only a good refrigerator, but you know, you got to insulate that refrigerator, right? And so we actually use the light to also keep these atoms from going and bumping into all the hot walls and things around it, in the same way a thermos bottle keeps you know, things that are cold, or the insulation on a refrigerator from.
So actually your atoms aren't touching anything. They're being
They're just being
suspended in
isolated
space.
from the rest of the room or
And
the
in
rest of the
fact,
apparatus.
we really do, we have sort of the world's best thermos bottle. So by using the light to hold the atoms in a certain place, but if they ever try and move out of that place, and if they ever try to have any motion, then these photons go and bounce off them, shove them back in, okay? In the next slide, you can actually see it doesn't take all that complicated an apparatus to do it, at least not after about 10 years of work. Here's a picture of our actual apparatus. There's a little glass cell here. You can see the outlines here in gray. That's about an inch, that size here. This is magnified up, so this is about an inch across. And we send light beams in, these red beams here, you can see coming in from all 6 directions. And then we get rid of all the air inside this cell, because we don't want air molecules bouncing into our atoms and heating back up. And we put in just a few of these very special atoms called rubidium. It's a kind of metal that's similar to what's in these yellow street lights, the sodium lights, okay? We shine our laser beams onto those atoms, and then we hold them, and you can see this ball in the center to signify that looks much like our rubidium atoms do once the light's holding them there, getting them very cold. And because there aren't any other atoms around to bump into them, there's nothing to touch them, we can get them extremely cold.
Now, how do you get all the rubidium atoms into the very center of your cell where the lasers can hit?
Well, actually, I haven't drawn this quite right. The laser beams are bigger. They take up the full space in here,
Oh, I see.
and all the way across the cell, and push it into the middle. This is artistic license here. I should say, so there's this little glass cell. You're probably wondering what these green and blue things are. Those are actually coils of wire that we use for the next stage of cooling, because unfortunately, just using laser lights like this isn't good enough. But I should show you what this really looks like in practice. If I can show the next slide, we get this little ball. So this is a real photograph of one of these glass cells, and again, it's an inch across here. You see that bright little speck in the middle there? Okay, that's about 10 million atoms, and they've got streams of light hitting them, just like these ping pong balls, bouncing off, and we see that light that's bouncing off, and so that's why this shows up as this bright little white ball in the center. Now,
So that's the condensate right there.
no, we're way away from the condensate still. What we've done here is a big step towards it, though. We started out at room temperature, which is on this absolute scale is about 300 degrees above absolute zero. This little blob there is cooled down to about 10 millionths of a degree above absolute zero. So you've got it incredibly cold here. It finally got onto the scale of my second thermometer, but unfortunately it's,
Still has a ways to go.
yep, it's 100 times too hot for the,
How long does it take to cool down from room temperature down to a few millionths of a
yeah,
degree?
well, it's pretty fast. It is about 1/10 of a second,
Really?
a little less, yeah. You can see this doesn't look like a big, complicated, expensive piece of apparatus, right? And in fact, it's not.
Looks like something you can build in your garage.
Yeah, you just about could. In fact, we have it now so that the undergraduate students in the physics department do this experiment as part of a regular course. One of the key things on this is to use really cheap lasers. The lasers people used to use before we started working on this cost about $200,000 roughly. And we figured out how to do this with really cheap diode lasers, the same kind as in your compact disc player or in this laser pointer I was using. You can see they die off though, just like my laser pointer. But that really makes it inexpensive.
Boy, that's really amazing. Kachun and I were both physics undergraduates just a few years back, and this concept was still like the holy grail of physics back then. And now students can do it as experiments. That's really amazing.
How much did the total experiment cost?
Well, I mean, I've only told you half of it. You know, this is the laser cooling and trapping part, and the total cost, somewhere in the ballpark of $50,000 to $100,000. It's hard to count because mostly it's students' time that we pay for rather than equipment. But so you thought this was the Bose condensation, but like I say, it's 100 times too hot. The reason, what's happening is that there's all these photons hitting the atoms. Even though that's not a very big push, it's still enough that it keeps them shaking around just a little bit. And so we discovered that, and we figured out we had to find some way to make them colder. We knew we had to get them much colder for Bose condensation. And so in the next show, I'll be talking about how we figured out to do the next stage of getting them cold enough to actually see them Bose condense.
Okay. All right, let's have the lights back on. That's great.
So I think we have a little bit of a background as to the actual experiment that was done by Dr. Wieman. And make sure you tune in for the second part, part 2, running all next week. We can talk about the actual details of the experiments, and there's more great demonstrations to go.
Yeah, don't miss next week because we're actually going to go on and use some real liquid nitrogen as part of our demonstrations.
Big time science here in the
so
studio.
if you want to see lots of liquid nitrogen and stuff getting really cold.
The picture of a real Bose-Einstein condensation.
Yeah, we can see the real line. That was just the teaser right there.
Yeah.
Well, we still have a few more minutes. Do you have another
Yeah, well,
question about the concept?
Oh, let's see.
Well, there's a question that sometimes comes up, especially to experimental physicists. And the question is, what is this good for in practice, in theory?
Well, at this point, it's just a very interesting new system to study. We can learn more about the laws of physics. If you get down on a tiny scale, of course, are different than what we see in the world around us. It's so-called quantum mechanics, and this effect we're talking about here is what makes it so completely different from what you're used to is that it's totally quantum mechanical rather than obeying the things of the world around us, and that's why it makes it so funny. And
it is physical confirmation of these sort of quantum mechanical theories.
Yeah, exactly. It's physical. It's physical confirmation of that, but it also allows us then to go further to study exactly how these things, how these laws, what they mean in terms of other systems. And in fact, in some ways, we're sort of getting a better microscope to explore that realm, and it's actually becoming quite important for applications like making electronic circuits, because they're getting so small, they're running into the laws of quantum mechanics in the circuits they build, and so we can now explore that.
It also applies to you've made something that as far as we had known, I mean, had never existed before in the universe.
Yeah, I mean,
And so that's sort of exciting in itself.
yes, I mean, it is, the universe around us is thousands of times too hot for this to exist, and as far as we know, except for people building it, it could never exist. So that's, you don't get to do that every day.
No, you don't. Yeah, it's amazing. I mean, a billionth as cold as space. That's
I don't want to think about it.
well. In the next show, we're basically going to be talking about how this experiment was done, and basically how the group at CU and the group at NIST were the first ones to be able to do this. And I understand there's somewhat of a sort of a competition or a race between various groups to be the first to do this. So
Yeah.
it's quite an achievement for CU to be the first to actually create this state of matter.
Yeah, I mean, there was a bit of a race, but it was, we actually started out way ahead of everybody else, and they sort of jumped in halfway along, but it was still unclear who was going to get there first, and so it was pretty nice that we could, especially because they were spending lots more money. So.
So this is another example of big science versus little science.
Well, it's all on the scale of giant accelerators. It's all little science. It all fits on a tabletop. You could see the pictures there, but
It'd be big science versus clever science.
Yeah.
but yeah. So next time I'll talk about these subtle details of this new cooling process we call evaporative cooling. How we use magnetic fields to actually be able to do that.
Okay.
Well, great. Well, I want to thank everyone for joining us from the first segment of this two-part series. We still have a few things to mention about the website. If you're interested in Bose-Einstein condensation, you can check out the Moment of Science website. The address for that is up on the screen, and there's links to the BEC server, which is the Bose-Einstein condensation server at CU, as well as a variety of other sites, Bose-Einstein condensation sites.
From other researchers working on the project.
And you can see previews of the next segment also to come there as well, about some of the experimental equipment and stuff. And I believe on your server you actually have a camera that's hooked up, so you can actually constantly monitor the people on the web can actually constantly monitor at the laboratory.
That's right. You can see what's happening each day.
Yeah,
I'm sure there's a lot going on every day.
Yeah, it's worth the perusal if you're out there surfing the net.
Oh, and also, there's actually one typo in the web address. There's the little dash in front of the Kachun in the web address is actually supposed to be a tilde, but we couldn't get the toaster to
So
make a little tilde.
That's a tilde down there.
Yeah. Where is it? Like right here?
Yeah, and if you have any questions or any comments on the program, please feel free to email Kachun and I. Our email addresses are also on the screen, and we'd really like to hear from you. Unfortunately, this session we weren't able to take calls live, but 2 weeks from now we'll be back in the studio taking calls. So we look forward to hearing from you then. And thanks for joining us.
All right.
Thank you, Dr. Wieman.
Thank you, Dr. Wieman.